While perfect. Hi, everyone, and welcome to today's webinar, MEP 2040 from Guidelines to Implementation. Thank you all for joining us today. My name is Huda Al Khatib, and I'm a part of the CLF Toronto Steering Committee. I'm here with Anya Barkan, who is co-programming lead at CLF Toronto as well. Um, Before we get started, you're going to see a poll pop up on your screen. If you can take a minute to answer it, that would be great. Here we go. Okay, I'm going to talk a little bit about CLF before we get started. So the Carbon Leadership Forum is a global network of over 5,000 members with representation from over 2,500 companies in over 75 different countries. Our focus is embodied carbon and how we as a global community can reduce it. So yeah. And if you haven't been to our events before, CLF Toronto is a local hub of the Carbon Leadership Forum. There are three other local hubs that currently exist in Canada, um, Vancouver, Ottawa, and Calgary. We host monthly events to share knowledge, connect people across the industry, and help build momentum around embodied carbon and carbon action in our region. So if you'd like to hear more about our events or stay in touch, please visit our website, clftoronto.com, and LinkedIn. We post events there and also sign up to our mailing list. And we have our email there on the screen if you'd like to also volunteer or be involved in the next events, or if you have any ideas, please reach out. We're more than happy to include you. As a Toronto-based group, we acknowledge the land we are meeting on is the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabeg, the Chippewa, the Haudenosaunee, and the Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis peoples. We also acknowledge that Toronto is covered by Treaty 13 with the Mississaugas of the Credit. Some housekeeping before we start. Feel free to type your questions in the Q&A box throughout the webinar. There will be time at the end of the presentation, around 10 minutes. So yeah, we can answer your questions then. We ask that you keep your videos and mic off until the question period. And this session is being recorded and will be uploaded on our website for your future use. And finally, today we are joined by Rachel Wrublik, who is a mechanical engineer at PAE and is a member and current vice president of the MEP 2040 Data Analysis and Reporting Working Group. She will introduce the MEP 2040 challenge and its mission briefly, and then highlight the beginner's guide and the upcoming version 2 update. She'll then provide an overview of the whole life carbon pilot study and ongoing findings and gap analysis. We will then be hearing from the Stantec team. Rina Anand will then introduce the initiative and workflow, followed by Aditya Patel and Poonam Kula, who will share the methodology, results, and their challenges when doing this case study and all the lessons learned. It's a healthcare pilot case study. So yeah, I'll hand it off to Rachel now, and she'll take us from there.
Great, thank you. Let me share my screen here. All right, can you all see my screen? Good. All right, so at the end of 2020, the Carbon Leadership Forum issued the MEP 2040 Challenge. This asks system engineers to advocate and achieve net zero operational carbon by 2030 and net zero embodied carbon by 2040. So this is not a small challenge, but from this, the MEP 2040 movement was born. We have a volunteer group of engineers and organizations that came together to form a mission to radically reduce total carbon emissions associated with building systems through collective action. We currently have 109 signatory MEP firms and 78 supporting organizations. We hold quarterly forums, which everyone's welcome to attend. We have a website, MEP2040.org, has a lot of excellent resources. And then we have links to several of the active working groups that are advancing our mission. So when we started in 2021, MEP was largely missing from the embodied carbon table. There was no MEP embodied carbon inclusion in LEED or ILFI. There were very few environmental product declarations out there. There was no US-based whole life carbon standard. The Carbon Leadership Forum material baseline didn't include MEP systems, and the V1 benchmark did not include MEP. So uh, we to start to fill this gap, within a couple years, the Data Analysis Working Group was launching the creation of the Beginner's Guide to MEP Embodied Carbon. And then while the guide was still under review, we launched a whole life carbon pilot study, which tested out the guide. This gave us an immediate feedback loop to work on V2 of the guide, make some really good improvements, and at the same time, QC the pilot data and work on a pilot findings and gap analysis. So as you can see with this timeline here, both of these are due to be released soon, with the V2 Beginner's Guide, hopefully of April of this year, followed shortly by the findings and gap analysis. Okay, so the beginner's guide was intended to help fill the gap in the lack of MEP specific embodied carbon guidance. It was a cross-industry collaborative effort. The guide gives guidance on how to perform quantity takeoffs and handle the LCA module calculations. It also presents a single whole life carbon MEP study. This is Weimer Hall. However, it is not inclusive of all system components. There are exclusions, which we list, such as air terminals. And it is also not a benchmark for MEP whole life carbon. Okay, so I'm going to go through briefly the guide on a high level. You can see here all the categories that were included, and then some of the specific pages for those categories. On each of those, we list some of the exclusions. We were really trying to kind of get to that 80-20 to tackle the most important big things that we could. And then within the guide, you can see that there is guidance around how to handle the takeoffs, mainly from Revit, and then assign them actual materials and embodied carbon data and handle those calculations. We also go through across the phases and give specific guidance of how to handle each of these. There are some specific exclusions, which is also listed. And then we have our uncertainty calcs at the end. And as I said, we have one case study that was included in the guide. And so high level picture of what we found out of that Weimer Hall study. We saw when we looked at cradle to gate upfront carbon, we saw that MEP accounted for more than a quarter of the emissions, which was much higher than a lot of the initial estimates have been. So this is a little surprising. When we look then at a whole life carbon embodied specifically, we see that MEP jumps up to over 50% in this particular case. This is once we're including replacements and fugitive emissions. And then the graph at the far right, we can look at the entire whole life carbon picture, which includes operational and water emissions, or energy and water emissions. And if we lump that into MEP, then we see that it's almost 3/4 of the emissions. So very significant, and really spoke to us in terms of the need to do something about this and get more data. Within the guide, there's a number of insight pages. We look at the EPDs that are missing from the industry. We really have a lack of carbon data in MEP. There's call to action pages with 4 different audiences. And then we look at sort of comparative impact of MEP materials, which I want to zoom into here. This table at the right looks at structure, enclosure, and MEP, and you can see the mass in the second column. Structure definitely outweighs everything, and thus it has a really large impact. But one thing we see with MEP is even though it's lower in total weight, it has a higher, or in this case study, it had a higher upfront embodied carbon impact than the enclosure, even though it weighed less. And that has to do with the complexity of MEP systems and the prevalence of electronics and metals and those complex components that increases the embodied carbon impact per kilogram. And then you can see at the bottom there kind of an example of that. The ratio on the right is kind of an average. But if we looked at, the steel or aluminum, these are things that are featured often in MEP, and just how important those material selections can be in overall impacts. We also talk about environmental product declarations. There's definitely a lack of those in MEP, but that is changing. We're seeing more and more of them. And one thing we saw looking at the whole life carbon picture is that for the case study, we were using more than 60 EPDs to cover MEP systems, which is much more than structure needing about 5 and envelope less than 15. So this speaks to the complexity of the systems. There's a lot of nuances to it, and really the importance of trying to get more embodied carbon data. So we also launched the whole life carbon pilot while the guide was under review. We recognized the void of MEP embodied carbon takeoffs in the industry, and thus embodied carbon data. And so this was a cross-industry collaborative effort by 27 companies. We got 20 individual project studies across varying typologies. And this was a great proving ground for the guide and the methodologies within it. And it is not, like I said, a benchmarking study, just like the guide was not. It is that initial data and testing out of the guide. And it's not inclusive of a very climate zone or typology or system type. We did the pilot study. We met weekly. It was a great group of organizations that met, volunteered their time to put together these case studies. And you can follow this from our resources page or find us on YouTube. And so out of these two big initiatives, we have kind of upcoming here, we have the V2 guide. This is set to release Earth Day of this year. Some good updates, mainly kind of coming out of that pilot study. And I'll give a brief overview of that here in a sec. And then the pilot analysis, where we're looking at our findings and doing a gap analysis, which we'll publish probably in May or June. And we will feature these findings in our next quarterly forum. That's May 14th. So I encourage you guys to attend. And yeah, so as far as the guide 2, this is the highlights. I'd say it's not fully inclusive of everything that's being updated. We are including metric formulas now in the guide. There's a simplification of the wiring takeoff. We updated the uncertainty calculation to align with 240p and added a template to that, so to help with that calculation. We have some good FAQ, a whole FAQ section that talks about district energy, how to use the guide outside of North America, how to handle refurbishment, and so on. So really excited about this. I think it's all good updates, but the overall structure is the same. Okay, and then just to close out here, a look back at our timeline where we're at. Really wanted to highlight that while we've had so much to do, and this seems like a very daunting task, we've made a lot of progress in just a few years. And few things, ILFI zero carbon certification now requires MEP 2040 participation. There is now a MEP EPD lead pilot credit for V5, which is pretty exciting. ASHRAE 240p is underway, and there is some talk within the Carbon Leadership Forum to include MEP. So with that, I will turn it over to the Stantec team to give you the results and discuss their pilot study or their case study.
Yeah, I will just share my screen.
Thank you so much, Rachel. That was insightful as always. So basically, good morning, everyone, and thanks for joining us. We're here today to share insights from our participation in the MEP 2040 Whole Life Carbon Pilot Study. We specifically contributed to a healthcare facility project as the case study. And the goal is not really only to show the numbers, it's to talk about what actually drives the MEP carbon and how our design teams can realistically make a difference. We also like to start with every presentation with a quick safety moment, and we specifically chose one today that would reflect how we can all be part of solving solution, how we can all be part of carbon reduction. So when you think about reducing carbon in your personal life, it's really one big action. It's really a series of choices that can add up over time. So there are 7 themes that you can see here on the screen. They start from driving to home energy, food, recycling, traveling, fashion, and water. The carbon outcomes, again, can be shaped by as many decisions as you can do. The correct decisions really applies to your daily actions, to buildings, to MEP systems, and you do have an opportunity to reduce carbon, and it starts early on. Okay, with that, we can move to quickly introduce ourselves. So I can start quickly. My name is Gina Anan, and I'm the Decarbonization Business Lead at Stantec. I'm honestly passionate about bringing in clarity, helping teams and clients do the informed decisions around reducing whole life carbon, about strengthening resilience, and most importantly, optimizing indoor environmental quality. I do work with an amazing team. Aditya, please, would you like to introduce yourself?
Yep. Thanks, Sheena. So Aditya Patel here, Associate Sustainability Consultant and Team Lead based in Ottawa. As Sheena mentioned, like we have an amazing team here, and we are all passionate towards decarbonization. We work on several building typologies and infrastructure projects, focusing on like improving sustainability in whatever aspect of the project is. And today we are excited to present this MEP LCA case study. Pass on to Poonam.
Yeah, hello, good morning, everyone. I'm Poonam Kula, Sustainability Consultant at Stantec Ottawa office, passionate about sustainability, BIM, and architecture, and excited to present this MEP 2040 healthcare pilot study.
Perfect. Thank you so much, both of you. We'll move to the next slide where we wanted really to start off as well with showcasing all of our building commitments. We do represent the building teams, and we have multiple commitments. They vary from AIA 2030 commitment, AIA Materials Pledge, SE 2050, but also we as Stantec team, we are committed to MEP 2040. So basically, that entails us to reduce total carbon emissions associated with MEP systems through education of our teams, through introducing specifications and various other items. So we do believe that participating in the pilot study is one of the ways that we can translate this commitment into practical and also project level insights. So again, glad to be here. We'll jump to the agenda on the next slide and we can tell you more about what we will be covering. So we will start off with a whole life carbon pilot study overview. We also will be speaking about what is life cycle assessment. I know Rachel touched on this in details, but we'll just go over it quickly. What is the MEP LCA scope, project introduction, the methodology, and then we'll definitely have some exciting slides around the results. But above and beyond, so we've done this pilot study, but how can we ensure that we're really showcasing that expertise in-house and applying it on other projects? So what we've done is have highlighted a lot of challenges, but also the solutions, and we'll tell you more around how we've addressed those across completing this study. Finally, we wanted to ensure that you're all part of this great effort. So we have some call to action, and then we'll open it up for discussion to hear more about your exciting projects. So with that, let's move to the next section, please, Banal. One more, please. Okay, so in talking about the MEP Life Carbon Pilot Overview, this is, again, an industrial collaboration. It's launched in early 2025. It brought in a lot of firms, 35 firms across 40 projects. And the intent was basically to understand the carbon across the full life cycle of MEP system. And this hasn't been historically well captured. So here there's a lot of value in this great effort. And now what we're trying to do here today, this presentation will present an overview of this pilot study. We've completed this effort last summer, along with ongoing findings and gap analysis. We really want to focus on this study undertaken as a healthcare facility and see how we can cater for it in other projects by understanding the methodology, by understanding the results, mapping those out, understanding the challenges and the key lesson learned. So we'll move to the what is the life cycle assessment and what are we capturing in our study. So before we speak about the project, we really wanted to understand what is LCA scope. So here we've showcased this wall building life cycle assessment. As you can see, it shows you the stages, A1 to A3 representing the stage phase, A4 to A5, the construction phase, B1 to B5, the use stage, C1 to C4, end of life stages, and then finally the D stage, which represents the benefits and load beyond the system. In every project, it's really important to define the boundary. It's really important to understand a common methodology so you understand what are you measuring from an embodied carbon perspective when it comes to the building. What are you evaluating? What are you including in that? And you're looking at it over the whole full life cycle assessment, not only from material extraction related to the building envelope, but how can you integrate MEP systems to get the full picture of your projects. So with that, we'll move to the MEP LCA scope. And this brings us really to the scope that we have looked at. So for this project, can move to the next slide, our scope covered key life cycle stages that are mostly relevant to MEP system. So for transparency, that include the product stage from A1 to A3, along with the transport A4, and then A5.3 as all highlighted in red, and the waste management under A5, construction and installation. When we move to the in-use stage, we've included the refrigerant-related fugitive emissions, B1.2 related to maintenance, B2 repair, and B3, and replacement B4, as well as operational energy B6 and water use, which is B7. Finally, we captured the end-of-life impact through the transport of C2 and disposal of C4. So together, this allowed us to capture the impacts A1 through C4, where MEP systems are mostly significant. And this is captured we follow the methodology and we work closely with the Beginner's Guide MEP team. So this is a great reference, which you can download for free from the MEP 2040 website that would give you a lot of these insights. So for now, we'll let you jump to the exciting project introduction and then results, but I'll pass it over to Aditya. Thank you.
Perfect. Thanks, Sheena, for kicking us off. So I'll go over the project introduction and methodology, and we'll dive into the results and later on the call to action. So as I can start off with saying this project again is confidential, so I'll not be sharing project location, but for all of you to know, this was located in an extremely hot and humid climate zone, which is ASHRAE Climate Zone 0A. This is a new construction healthcare outpatient facility pursuing LEED Gold. Uh, it is roughly 4,500 square meters in gross floor area. It's one story above grade with a building height of approximately 10 meters. This assessment was done at 100% construction documentation stage. Again, it's more of an accounting exercise we did on this project to capture the MEP carbon footprint. But ideally, like you would expect such studies to be conducted from early on in the schematic design and moving on through the other design phases. Overall study length was 60 years. The tool we used for conducting this is one-click LCA, supported with spreadsheet-based calculations using TM65. There are several codes, local codes and ASHRAE codes that were referenced for this project. Will not go over the envelope details, but window to wall ratio for this project was 33%. Yeah, the key things, mechanical systems. So as I mentioned, this is building is located in an extremely hot and humid climate zone, so it's cooling dominated. We have 3 air-cooled cold chillers supplying nearly 1,500 tons of cooling. Heating is provided by electric boilers, just over 100 kilowatts of heating capacity. For air side, we had 3 HUs, all having energy recovery ventilators and terminal VAV units, supplying a total of roughly 100,000 CFM. We have backup diesel generator, electric water heater, and throughout the building, we had low flow fixtures. Another interesting thing to note is this project did have on-site renewables. So, and we did assess the carbon footprint of that. Yeah, moving on to the methodology. Next slide. Perfect. So this slide shows like how we actually calculate the MEP carbon footprint. So it starts with confirming the level of development. Now, what does this mean? It probably means the BIM execution plan for the project. So we understand like what level of details is modeled in Revit. We coordinate with the design team members to understand uh, how much details we can extract from the BIM models. Again, we started this project later, like at construction design, so we had a lot of good information to extract from. If you are starting early, there would be more collaboration required between the design team members to understand like what details are being modeled versus what is left out at the schematic design phase and what you need to consider. Next step involves performing takeoffs. So once you establish there's good enough detail in the Revit models, you start doing takeoffs for MEP systems. Again, this is mostly Revit based, supported with like step 3 again is something critical, which defines materials and properties. So takeoffs doesn't mean you have the right information for conducting LCA. You might have piping length but not the material. You might have number of boilers but not the capacity, right? Things which Revit models might not have. You need to refer back to product cut sheets and specifications to establish like the mapping between the material and equipment project uses and their properties. Once you have all those takeoffs established, you'll move on to identifying material emissions data. This is where you'll need to do research, right, on available EPDs and data points which are applicable for your materials and equipment. And again, there would be gaps, and that's a reality. So you need to come up with like alternate solutions as well. So step 5 is basically calculating the MEP carbon footprint. So as I mentioned, we used one-click as a primary tool supported by spreadsheet calculations. The TM65 approach was used again to either validate or populate the gaps where we see like there wasn't valid data points available. So it's important to note that uh, because this is something very new, you don't trust the calculations. You find multiple ways to do the same calculations and try to arrive at similar values or understand why there is a difference between the values, right? And that's why the step 6 is very important: quality assurance and sensitivity analysis. So we identify anomalies with takeoffs, uh, selected EPDs and data points. Sometimes Revit model might have very high takeoffs, right? For certain elements, it might assume solid volume and elements might be hollow, for example. Things like that might occur. So you do need to have to go through the process to understand uh, which approach or methodology is applicable for the takeoffs, and yeah, and move forward. So now I will pass it on to Poonam to go over the results.
Thank you, Aditya, and good morning, good afternoon, everyone. And now let's take a look at the embodied carbon results for the MEP systems at the product stage, which is basically cradle to gate. So this slide gives a high-level snapshot of where the embodied carbon is coming from. What you are seeing here is the breakdown by discipline, which is expressed on an intensity basis. We can see that the mechanical and electrical systems stand out together, account for 70% of the total impact, while plumbing contributes the least. It's important to keep in mind that these results are project specific and the embodied carbon intensity can vary for each project depending on factors like building location, system selection, and other design decisions that are unique to each project. And to talk about the scope for these numbers that you see on the screen, the scope includes, for mechanical, the scope includes ductwork, piping insulation, and mechanical equipment. Electrical includes wiring, electrical equipment, and lighting fixtures. Renewable includes solar panels only, and fire protection includes piping, and plumbing includes piping insulation, and plumbing fixture. And we can see that the total carbon intensity for all these disciplines is at 226 kilograms CO2 equivalent per square meter, and associated carbon footprint is 1,219 tons CO2 equivalent. So overall, the key takeaway here is that the mechanical and electrical systems dominate the embodied carbon footprint. And in the next few slides, we will dive into each discipline results and see what's driving these numbers and why some of these are higher and some of these are lower than others. So let's look at each discipline individually. The first one is the mechanical. And in this slide, from the bar graph at the bottom, we can see that the ductwork is the single largest contributor, significantly outweighs mechanical equipment. This is happening because the project uses an air-based HVAC system, which naturally requires more ductwork, which makes the ductwork the heaviest category overall. And another reason for such high emissions is that the ductwork was fully modeled in Revit, which increases the confidence in the results as we had to make more assumptions. Therefore, we can see the total carbon intensity for mechanical is at 93 kilograms CO2 equivalent for cradle CO2 equivalent per square meter for cradle to gate, and total carbon footprint is at 504 tons CO2 equivalent. Yeah, so this slide focuses on the mechanical equipment. We have 6 or 7 major categories, and one key insight here is that AHUs alone contribute nearly twice as much as any other equipment. So basically, in total, like the building used 3 AHUs with a combined total supply airflow of about 100,000 CFM. And the VAV terminals are also contributing, like they are the second largest contributor, and there were total 320 VAV terminal units distributed throughout the space. And the others, like hot water chillers, fans, fan coil units, they are also contributing, but they are not as high as AHUs or the VAV terminals. So overall carbon intensity was at 25 kilograms CO2 equivalent per square meter. Now, looking at the electrical discipline results, we can see, based on the category contribution, from the bar graph, we can see that the electrical equipment has the highest category contribution at 72%, followed by light fixtures. And wiring contributes a smaller share, almost like 10%, offering limited reduction. So we can see that the total embodied carbon intensity across electrical is at 67 kilograms CO2 equivalent per square meter. And in the next slide, we will understand what's driving these numbers in the bar graph for electrical discipline, like why the electrical equipment has the highest category contribution when compared to lighting fixtures and wiring. So as you can see from the bar graph, the generator dominates the embodied carbon at 33%, followed by UPS and batteries, and then transformers. ATS is the least contributing category. So the total carbon intensity is at 48 kilograms CO2 equivalent per square meter for cradle to gate. And the reason why systems like generator, UPS batteries, and transformers dominate the electrical equipment is because they are material intensive and carry a higher embodied carbon footprint. So looking at the wiring embodied carbon results, we can see that the cable tray and wiring together account for like 90% of the contributions, where cable tray is at 47%, and the total carbon intensity is at 7 kilograms CO2 equivalent per square meter. for A1 to A3 stage. Looking at the plumbing results, it can be seen that the plumbing embodied carbon is overwhelmingly driven by piping plumbings, and plumbing fixtures contribute a much smaller portion. Overall carbon intensity is at 12 kilograms CO2 equivalent per square meter, and total carbon footprint is 68 tons CO2 equivalent. Looking at the fire protection, this one is interesting because when we look at the graph at the bottom, which basically compares the fire protection piping with the plumbing piping and the mechanical piping, we can see that the fire protection has the highest carbon compared to mechanical and plumbing piping. The reason for that is because this higher carbon intensity is due to the fact that in the Revit, the model was comprehensive. Not only branch pipings were modeled, but not only the mains were modeled, but the branch piping was also modeled. So that is the reason we see like piping fire protection has the highest piping contribution for fire protection. And the total carbon intensity is at 26 kilograms CO2 equivalent per square meter, and total carbon footprint is at 137 tons of CO2 equivalent. So the material for piping fire protection was carbon steel, and for plumbing piping, it was stainless steel and PVC, and same for mechanical, it was stainless steel and PVC. Yeah, so renewables is another exciting discipline. So when we look at the renewables at the bar graph, we see that it doesn't fall at the top or at the bottom, it falls right in the middle of the pack. And basically, the solar adds upfront embodied carbon of 27 kilograms CO2 equivalent per square meter. One thing to note here is that the inclusions, the scope for renewables was only PV panels, and we excluded inverter mounting systems, pedestals, optimizers, PV wiring, electrical disconnects, and combiner boxes. So basically, solar is an investment that pays back through reduced operational emissions, which we will look at in the next few slides. So this slide summarizes A1 to A3 results, and we can see the top 10 contributors, with ductwork being the highest at 26% and photovoltaic panels at 12%, followed by fire protection and so on. Yeah, so now I will pass on to Aditya, and he will discuss whole life MEP embodied carbon results. Thank you.
Perfect. Thanks, Poonam, for going over the cradle to gate results. As you can all imagine, each category has its own nuances, takeoffs, and selection of EPDs or data points, and there are several assumptions that go behind them. So again, as we move forward, I'll present the full life cycle stage results from A through C. So this bar chart is very interesting to see. You can observe that we already covered A1 through A3, right? So it had an intensity of 226 kg of CO2 per meter square. If we look at the full picture, the overall intensity is coming out to be 872 kg of CO2 per meter square. And this is just for MEP, right? Very, very significant. Now, two things that stand out: refrigerant emissions, which are fugitive emissions happening over the course of the life cycle of the building. As I mentioned, this was a cooling dominated climate. We had a lot of refrigerant use on the project, resulting in very high emissions for that category. I'll go over slides where we cover like refrigerants specifically. Another thing, B4, right, which are replacements. As I mentioned, building services have a lot more frequency of replacements during the life cycle, which results in a very high emissions. So you can see that it stands out, 472 kg of CO2 per meter square as its category. So we'll next slide, we'll go into why this is happening. So this chart helps in understanding. Typically, when you do building LCAs, you would have seen that B4 emissions are not as significant, where you only include building structure and envelope. Reason is they're mostly long-lasting elements. They last beyond 60 years or greater than 50 years. Foundation would last probably, it's an everlasting component, right? But as you move inside the building, you would see The service life of materials and equipment reduces. So building services, if you focus on that, it varies from around 10 years to less than 50 years. So depending on the component, it might have multiple cycles before during our analysis length, right? So if you move to the next slide, this table captures like equipment service life for various building services equipment, and the number of equivalent replacements over 60 years. So as you can see, like pumps, inverters, batteries, as much as 5 times during the course of our analysis. uh, AHUs, fan coils, chillers, we had air cooled chillers, right? Boilers, electric boilers, as much as 3 times. Again, they could vary. I'm not saying replacements are subjective as well, right? These are typical values that were captured. If equipment is made to last longer, those replacements are less, right? Uh, and so on. So there are other elements. Perfect. So refrigerant impact, as I mentioned, this was a very significant contributor. It contributed 17% of A through C emissions with an intensity of 146 kg of CO2 per meter squared. We had two primary refrigerants, R454B, which has a GWP of 466 kg of CO2 per kg, and we had R410, which is a very high GWP of 2088. Based on the amount which leaks every year, it may be ranging from, I don't know, 1% to 3%, and then end of life and installation leaks, which are also very significant. And on top of that, there are replacements of the equipment, right? So all that contributes to very significant refrigerant emissions occurring over the lifespan of this project. So this is interesting. Like previously, we showed you like the top contributors when we looked at cradle to gate. We had ductwork, PV panels, piping for fire protection, and so on. But if we add like A through C, now there's one category which just jumps out. Refrigerant wasn't there. It jumps out to second category. So that's the impact, significant impact refrigerants can have on the building's carbon footprint. And it's very important to have right selections, right? Early stage informing the design on choosing refrigerants which are available, low carbon refrigerants, is critical. Perfect. Now we'll cover the MEP embodied carbon and operational carbon. So note that these results cover MEP component of embodied carbon and not the full embodied carbon covering structure and envelope. But regardless, you can see like if we look at embodied versus operational without solar, it's roughly 44 to 56% split. If we add the solar PV panels, it's roughly 55 to 45% split. Now imagine adding, this is just MEP as I mentioned, adding the structure and enclosure embodied carbon, it will be very significant. The results we are showing here is for year one. So operational emissions, on the next slide, you will see like over a 60-year period, they would add up. Uh, so probably Poonam, can you move to the next slide? Yeah, perfect. So here we see like those operational emissions. Again, they are the assumptions based on how we have calculated them. But just to show you like operational emissions, the project was in a dirtier grid, so that impacts significantly operational emissions. And we have assumed the grid intensity to be like fairly consistent throughout the study period, which might not be true, right? Every jurisdiction now has planned to decarbonize their grid, and over the course of like few decades, we'll start to see those intensities come down. But assuming it's a dirtier grid, it remains fairly consistent for the next several years before actually going down. Operational emission like has significant contributor. It's not to say embodied carbon shouldn't be the focus. It's more so for this particular instance, we have the split. Yeah, moving on. So yeah, we had presented the results again. A lot of different types of results we have captured: material level breakdown, equipment level, to capturing the full life cycle. And again, as I mentioned, like throughout the presentation, that there were several data gaps we have observed in the Revit model, Revit schedule challenges, limitations. So not everything looks as straightforward as doing takeoffs in Revit and assigning an intensity and calculating the MEP carbon footprint, scope boundary definition, like including certain elements versus excluding limited EPD availability in the market. That's a well-known fact when we are doing an MEP LCA. So, like how we went about it, again, it's a very collaborative effort. Designers or the BIM team needs to understand what we are trying to extract from the Revit model. We need to be clear in our request as well, like what we want, the level of details, and what we are trying to do with that. So, uh, and where there are schedule limitations, we need to build our own calculation spreadsheets. So there were manual calculations done using spreadsheet. Uh, Boundary definition is more so like, again, a coordination piece, and limited EPD availability is more, first, if we don't find an EPD for a particular manufacturer, we actually communicate with them to inform them or educate them that this is something industry is looking for, so they are aware. Uh, and we are seeing that, right, in the market, like suppliers now, even on lunch and learns, in our local team here, like we observe that they are more and more knowledgeable now with these requirements, and they're working towards them. So next slide. Yeah, solution. One of the things we have done at Stantec is we realized every Revit model, Stantec is a big company, like different, like all over the globe. We have different BIM teams working on different models. So we did produce an internal guidance document for our BIM designers and modelers on like a step-by-step guide to streamlining MEP Revit model development in support of embodied carbon assessment. This is something powerful, right? At We are trying to do this at scale, helping to do these assessments, streamlining them and doing it more efficiently. So this is a critical step where designers also need to understand their role and what they can do to support this effort. Yeah. Gina, I will pass on to you for call to action.
Perfect. Thank you so much, Punam and Aditya. Always great to work with an amazing team who put a lot of effort into this exciting project. Um, Really, on this slide, all we wanted to mention and say is that reducing MEP embodied carbon is a shared responsibility. And we do believe that every single discipline has a role. What we've laid out here is that manufacturers can really enable transparency, circularity, and low carbon innovation. Designers can drive the demand and integrate this whole life carbon thinking, like what we try to do on every single project. Clients' role is to set expectation, is to create that market demand. Contractors can deliver low carbon outcomes during construction. And finally, certification and policymakers have a role in making MEP embodied carbon measurable and mandatory. So I would only say that we can do so much. Feel free to reach out. We're really excited to push this further and do more exciting projects and apply this exciting methodology on more and more projects. With that, we would like to open it up and hear your thoughts. You're probably working on some exciting projects, or you would like to share some insights from what we just presented. So please feel free to add your questions. Oh, we do have some questions in the chat, and maybe Hada, would you
Yeah.
like to lead it from your end? Perfect.
Yeah, of course.
Amazing.
I'll read the questions and then feel free to unmute and answer. Michael Wong asked if you can share the size of the PV array that was used in the case study.
Yeah, so we have that info. It's 671 kilowatt capacity of PV. Yeah.
Perfect. Daniela is asking if there was an assessment also conducted on the typical base building scope. It would be interesting to see the comparison between impacts of structural and architectural along with MEP.
Yeah. So for a similar healthcare project in the same region, we do have completed structural envelope scope, and we feel like this number. Again, every jurisdiction or region in the globe has different building practices, and we see this number for MEP especially was really high compared to even our structural or comparable. Like both numbers were high, but MEP having such footprint is really like a thing to consider, right? Like we cannot exclude this type of analysis from our scope.
Maybe that's a part two for this or something. But yeah, it would be nice to see the percentages side by side, maybe.
Yeah.
But I can imagine they look really big and comparable to a structure. Um, Amanda is asking what EPDs were used to model the equipment, so chillers, air handling units, etc. Were the one-click generic EPDs used, or were you able to source product-specific EPDs?
Yeah, so the great question. Like again, it was a mix and match. With the region we are working on, we had limited EPDs available. Like for example, it was not in North America, right? So here we have manufacturers like Train, Daikin, whatever, right? They have more and more EPDs. We have similar like products specified there, but look, there were no like localized EPDs for such products, right? So we had to either use industry, I guess. Amanda points out like here, like there are generic EPD sources or industry-wide averages, but whatever's data point we pick, we do verify with another approach. So in the methodology, I was going over that TM65 approach. Like it helps in gauging like whether we are picking the right data point. Sometimes data points are also vague, right? They don't specify enough uh, on the capacity or the weight, or something is missing, which leads us to like lose the confidence in what we are picking. So it's coming up with multiple ways to calculate the footprint and ensuring that it is reasonable, right? Okay, this is by weight of this component and the materials that are involved. Like you break it down. For example, if you have a transformer or a generator, you can break down into bare bone elements, right? Like steel, copper, XYZ, whatever is used, and try to estimate that way and see like where you end up. Again, there are several things which gets involved, but it's just trying to calculate different ways to end up with the same value or close to it.
Perfect, thank you. I guess maybe I have a question following up to this, Rachel. Would the results of those different MEP pilot case studies be compared? Like which data sets were used for each? Because I can imagine all different teams used different generic materials wherever there were lacking EPDs. So will those be compared, like similar to creating like the carbon leadership material baseline, right? Is there something like this coming for or in the thoughts?
We are looking at the spread that we're seeing of impact, especially the A1 to A3 per subcategory, each of these elements that we saw reported. But we're not going through and verifying each EPD or TM65 that was used. So we're kind of just going through and seeing, what it is on a per kilogram basis and per meter squared basis. And we'll have that in the findings.
Okay, nice. Great, thank you. And the last question we have from Anna was ASHRAE 240p used for calculating emissions?
Is that maybe a question on the guide or the case study? I guess I'll take a pass for the guide. We definitely referenced ASHRAE 240p. The first draft was out at that point. Also leaned on RICS. As we've done the V2 guide, more and more trying to align ourselves with 240p. It's a second draft, so the final isn't out there yet. And we try to reference that as well, so you can see that in the formulas and the tables.
Okay. If anyone has any other question, please feel free to unmute and ask. We can have a discussion here. Maybe a small question to Stantec from my end. Do you see MEP LCAs being implemented on more projects moving forward? And how easy will it be? Like how long
So,
did this take for your team, I guess, is maybe another question.
So within Stantec, there's a lot of support towards research efforts and work. So we were supported to do this effort on an existing project that we were doing lead certification on. I do believe that it's on our responsibility to educate internal disciplines and clients that this is an opportunity that they can take today. So internally, I think our goal at the moment, after we've highlighted the challenges and the opportunity, is to try to streamline it as much as possible through the workflow. It does not happen overnight for sure, but this is a goal we're definitely working towards. And it's not an answer of yes or no. It depends really on the market. It depends on the location, on what we have available to put it together. But we don't say no for challenges. We take those and move forward. I also want to flag being active with MEP 2040 on the steering committee that there is now on the MEP 2040 landing page list of manufacturers that have EPDs. So feel free to check those out. They're constantly being updated. You don't find the EPD there. You just find the manufacturer or supplier that could have potentially that EPD. So make sure to utilize that opportunity because you might have those information in front of you and utilize them as needed. So I hope I answered your question here, Huda.
Yeah, you
one
did.
more thing to add to Gina's point, like again, this is recently, like we did have a request, one of our clients requesting this service. I cannot share more details, but they had modified their specifications to include as an optional scope, and they're trying to do this as a pilot for a couple of their projects. So like projects are in DD or construction design phase, but again, as I mentioned, this is more so they want to capture this on their project typologies and see where it takes. So
Yeah. Okay. This brings us to the end of the webinar. If anybody has any other questions, please feel free to email us or the presenters with your questions. And thank you so much for our presenters for doing this and being a part of the webinar. It was really insightful. So yeah, I'll conclude it. And hopefully there's a part 2 when everything comes out and we take a look all the pilot studies and the version 2 of the guideline. So we look forward to that. So thank you so much.
Thank you so much, Huda and
Thank you.
CLF team.
Yeah.
Appreciate
Thank
it.
you.
thanks all.
Bye.
Bye.